Chemical reactions and energy. The final section. Lesson objectives. You're going to describe endothermic reactions. You're going to describe exothermic reactions. Relate the law of conservation of energy to chemical reactions. We will not define activation energy or identify factors that affect the rates of chemical reactions. Those two objectives we will not necessarily need to do, but we'll look at them. The vocabulary for today. You can see several terms here. Some of them are on your list in your reaction notebook, some of them are not. Introduction. All chemical reactions involve energy. Energy is needed to break bonds and reactants. These bonds may be very strong. Energy is released when new bonds form in the products. That's because the atoms now have a more stable arrangement of electrons. Which energy is greater? That needed for breaking bonds and reactants, or that released by bonds forming in products? It depends on the type of reaction. When it comes to energy, chemical reactions may be endothermic or exothermic. Endothermic reactions. In an endothermic reaction, it takes more energy to break bonds in the reactants than it is released when the new bonds form in the products. The word endothermic literally means taking in heat. A constant input of energy, often in the form of heat, is needed in an endothermic reaction. Not enough energy is released when products form to break more bonds in the reactants. Additional energy is needed to keep the reaction going. The general equation for an endothermic reaction is not found here. Anyway, in many endothermic reactions, heat is absorbed from the surroundings. As a result, the temperature drops. The drop in temperature may be great enough to cause liquid products to freeze. That is what happens in the endothermic reaction at this URL. Check it out. One of the most important endothermic reactions is photosynthesis. In this reaction, plants synthesize glucose. Synthesize just means to make. So they make glucose from carbon dioxide and water. They also release oxygen. The energy for photosynthesis comes from light. Without light energy, photosynthesis cannot occur. The chemical equation for photosynthesis is also not found here. Plants can get energy that they need for photosynthesis from either sunlight or artificial light. Exothermic reactions. In an exothermic reaction, it takes less energy to break bonds in the reactants than is released when new bonds form in the products. The word exothermic literally means turning out heat. Energy, often in the form of heat, is released as an exothermic reaction occurs. The general equation for an exothermic reaction is not found here. The energy is released as heat. An exothermic reaction results in a rise in temperature. That's what happens in an exothermic reaction at the URL below. So if we're looking at exothermic versus endothermic, these reactions, exothermic will feel warm or hot. Endothermic will feel cooler or cold. So this is kind of like an ice pack. This would be like a hot hand or a hand warmer. Combustion reactions are examples of exothermic reactions. When substances burn, they usually give off energy as heat and light. Look at the big bonfire below. You can see the light energy it is giving off. If you were standing near the fire, you would also feel its heat. Conservation of energy. Whether a reaction absorbs energy or releases energy, there is no overall change in the amount of energy. Energy cannot be created or destroyed. We've learned this. This is the law of conservation of energy. Energy can change form, for example, from electricity to light, but the same amount of energy always remains. If energy cannot be destroyed, what happens to the energy that is absorbed in an endothermic reaction? The energy is stored in the chemical bonds of the products. This form of energy is called chemical energy. You've heard that before. In an endothermic reaction, the products have more stored chemical energy than the reactants. In an endothermic reaction, the opposite is true. The products have less stored chemical energy than the reactants. The excess energy in the reactants is released to the surroundings when the reaction occurs. The graph in the figure below show the chemical energy of reactants and products in each type of reaction. Notice in an endothermic reaction here, we have the reactants, that's the stuff going into the reaction, and the products coming out of the reaction. This is stored chemical energy, right? The reaction is moving along this direction. So the reaction starts right there. Energy is absorbed, and we have the products, right? So this might be carbon dioxide and water, and the plant undergoes photosynthesis and makes glucose and oxygen. The products have more energy than the reactants. In an exothermic, imagine a block of wood, a chunk of wood, and we give it a little energy to start it, and it burns, and then we have ashes. The ashes have much less energy than the original wood. All chemical reactions, even exothermic reactions, need a certain amount of energy to get started. This energy is called activation energy. For example, activation energy is needed to start a car. Turning the key causes a spark that activates the burning of gasoline in the engine. The combustion of gas won't occur without the spark of energy to begin the reaction. Also, imagine starting a lighter. You push the button, you have to give those first initial sparks to provide the energy to get the reaction going. Why is activation energy needed? A reaction won't occur unless atoms or molecules of reactants come together. This happens only if the particles are moving, and movement takes energy. Often, reactants have to overcome forces that push them apart. This takes energy as well. Still more energy is needed to start breaking bonds in reactants. The graph in the figure below shows the changes in energy in endothermic and exothermic reactions. Both reactants need the same amount of activation energy in order to begin. You'll notice this would be like the equivalent of sparking a lighter, right? This is the spark that's required, and then it starts burning. All right? You have probably used activation energy to start a chemical reaction. For example, if you've ever used a match to light a campfire, then you provided the activation energy needed to start a combustion reaction. Combustion is exothermic. Once a fire starts to burn, it releases enough energy to activate the next reaction, and the next, and so on. However, wood will not burst into flames on its own. As you lit the match, you push down with a force and use friction to start the chemical at the end of the wood match. The match then began to burn, and that process just occurred. But the initial energy you gave was the friction and the sparking of that chemical on the end of the match. That's the activation energy. Any factor that helps reactants come together so they can react lowers the amount of activation energy needed to start the reaction. If the activation energy is lowered, more reactant particles can react, and the reaction occurs more quickly. How fast a reaction occurs is called the reaction rate. Factors that affect the reaction rate include temperature. Typically, higher temperatures make the reaction go faster, concentration of reactants, the surface area of reactants, and the presence of a catalyst. So I'm not going to read the last part, but we can observe the temperature can affect reaction rates, concentrations, surface area, and the presence of a catalyst. All right? Thanks for listening.